Hi everyone, welcome to week 2, the Unit 1 and 2 chemistry seminar. We are effectively cramming 40 weeks of work into 10 hours. So we will be getting through a lot, but the advantage is I don't have to hand it to all the crap they do in the schools for grade 11. Just teach you exactly what you need to know, exactly what you don't need. Well, I won't teach you what you don't need to know, obviously. And again, I'm just going to use whiteboard. There will be some materials tonight because there is some visual stuff with the mass spectrometry. But for the most part, I will just be using the whiteboard like I'm about to now. Still haven't learned how to draw. That will never change. Algebra, if anybody's interested. So, an isotope. I'm going to start by talking about isotopes. We know that, well, I hope everyone knows by now, the basic atomic structure. We have nucleus, with neutrons and protons. Then on the outside we have electrons. There is supposed to be a balance between the neutrons and the protons. If we take away a electron, then the charge of the atom will change. If we add or take away a neutron, then it becomes almost an entirely new chemical species. So we have carbon 12, carbon 13, then we have carbon 14, which is it's just radioactive. And the only difference is the number of neutrons. You may have seen represented like this. So, I think I may have touched on this last week. So we have the atomic number. Again, it's important to know what these numbers mean on the periodic table. So this number here is the atomic number, or the number of protons. You may see it also written as AZ, and then you have the chemical symbol there, or the element symbol, whatever you want to call it. So here is the atomic mass. So the atomic mass is the sum of the protons and neutrons. And when we're talking about isotopes, the atomic number would stay the same. But this Z number will change. So the isotopes have the same protons, but they have different number of neutrons. Same protons, different neutrons. Now this is really important to understand when we start talking about radiation and nuclear compounds and nuclear chemistry. So, isotopes, same protons, different neutrons. Let's take, okay, all right, I'll get rid of this if everyone's finished. So let's look at oxygen. Oxygen has a number of isotopes. So 16O. Has has 8 protons, so regular. Regular oxygen, 8 protons, 8 neutrons. We have 17O. So again, 8 protons, 9 neutrons. We also have 18O. 8 protons, 10 neutrons. So the only thing that changes in an isotope is the number of neutrons. Why is this important? It doesn't really matter for anything under element 70. But anything above element number 83 is radioactive. Everybody knows radiation, everyone knows what radioactivity is. Sorry, just my coffee. But it's this proton to neutron ratio, or N/Z ratio, that tells us whether something will be radioactive or not. Once you get above mass number 83, everything is radioactive. So after, I think it's, I can't remember what number 83 is now. That's good. That's a good start. So the further or the more off this ratio is, the more unstable the nucleus is. If you think there's only so much room inside the nucleus, you start adding loads of neutrons, the nucleus is going to want to get rid of some of those to try and come back down to a stable isotope. Now we'll go through more of that after this, when we start looking at radioactivity and sort of unstable elements. The isotopes have the same chemical properties, but will have slightly different physical properties. So meaning they will look slightly different. So carbon, the first of our unstable atoms, is carbon 14 or 14C. Carbon exists as 12C normally. So 6 new protons, 6 neutrons. Happy days. 14C, 6 protons and 8 neutrons. Sad face. We use, well, I mean, it's actually really handy because we use 14C for dating things, bone samples, organic samples up to 50,000 years old. So we can use the ratio between 14C and 12C to tell how old things are. Again, I'm not going to go too deep into that. But if this ratio is off, it is an unstable isotope. So 12C, 13C, all perfectly fine. 14C is unstable. So we can calculate all of the atomic mass units on the periodic table are an average, or an average AMU. Because when every element has at least one isotope, there might be a couple of exceptions to that. But for the most part, they have at least one isotope. So it all depends on the relative abundance of each isotope in the on Earth. Well, I guess we can't measure it against anything else except for on Earth. So we have the mass, and this definitely be on an exam for unit 1 and 2. Mass of isotope 1 times the percentage abundance. So the percentage abundance will be given to you. You would never be expected to know that. Plus the mass of isotope 2 times, again, its relative abundance in percentage over 100 gives us the average AM unit. So if you took a sample of carbon, it wouldn't be exactly what it says on the periodic table, because you would have all of the different isotopes somewhere in there. So let's look at magnesium. So magnesium has 3 isotopes, 24, 25, and 26. If we have, so let's calculate them all. There's 3, so we'll do them individually. 23.99 times 78.70% abundance divided by 100. Uh, 25 is 24, and that's 10%, I think. 0.13. 2.531. 26, that's not 26, it's 25.98. The percentage, what's left? 11.17. So we then add them together. And if someone wants to check the periodic table for the AMU of magnesium, make sure I'm right. Should be 24.31. So we need to know the isotopes because we need to know the average atomic mass. And we apply that across the board. Okay. Why is this important? 24.305, or rounded to 24.31. Why is this important? So we get into nuclear chemistry. We have three kinds of radiation. We have alpha decay, where there's so many neutrons that the element spits out an entire helium nucleus. So, spits out an entire helium nucleus. And it does this because when it has this many neutrons inside the nucleus, the atom is very excited and it needs to come back down to its normal state. And remember that N versus Z ratio, or N to Z ratio, between the protons and the neutrons? Above 83, every single element is radioactive. This stuff is harmless. A piece of paper could stop it. So the next one is beta decay. Beta decay is getting a little bit scary, but what it does is a neutron degrades to an electron, and the electron is spat out. So this is positively charged. Negatively charged. The last one is what we call gamma. Gamma decay. Now this is the one that kills. So gamma decay does not have mass, it does not have charge, it is just pure energy. So you can stop beta decay with aluminium foil. Gamma decay is pure energy. Gamma decay, pure energy. You need lead and concrete. And even then, the sarcophagus they built for Chernobyl to hold in the radiation has already started to be destroyed after 30 years. And it's now being replaced. Because the energy is so, the gamma decay is so high energy. Think of the sun, but kind of the sun on steroids. So they're releasing these kinds of radiation so they can go back to a stable isotope. Now, uranium 238 is the most radioactive element, and it will decay step by step by step by step by step back to lead. Only when it's turned itself into lead, Colombo, is it stable again. uranium-238 becomes uranium-235, becomes tritium, and so on and so forth until it gets down to lead. Now we can tell how old something is by utilizing this. There's rocks in Australia that have the very first bacterial fossils, and that's about 4.4 billion years old. It's the only way we know is by this method. So we have this concept called the half-life. So in 7.4 billion years, there will be half as much uranium than there was at the beginning. We know uranium decays into lead. So we can use the ratio, again, I'm not going to go too deep into it. We can use the ratio between uranium-238 and lead with this half-life to tell us how old something is. It's a very, very contentious scientific issue. A lot of people say we shouldn't use it because we can never prove that, but yeah. We can use radioactive elements in smoke detectors. So if you take apart your smoke detectors, most of them will have very small amounts of americium, I think it is. Okay. Any questions about isotopes and nuclear and half-lives? Okay. The next thing we're going to look at is emission spectrum. Or emission spectrum. Can't I find that? That's that. Diagrams. I'm not very good at drawing. So if you look at the old neon signs, not usually made out of neon anymore, but by passing an electric current through different gases, so neon, xenon, argon, helium. If we pass an electric current through these, we get an emission spectrum, an emission of light. From electricity. So flow an electric current through, and we get the emission of light. So when we're talking about energy, talking about electrons or electricity, sometimes when they absorb light. If we remember the structure of the atom, and we know that there are 7 electron shells because there's 7 periods on the periodic table. When an atom gets excited by, I'm pretty sure there's 7, if not, just pretend there's 7. When an atom gets excited by electricity, by some kind of energy, by sunlight, the electrons move to the higher energy levels. Regardless of where their electrons are, they will move out. Now, this is not what the atom wants. So the atom needs to lose some energy. Atom needs to lose some energy. Does this by emitting light. Now, lots of different elements will burn different colors. Same thing here. Different elements will glow different colors if you put electricity through. And this is called the excitation fallback theory. Ground state, so a little bit of terminology. The ground state of an atom is at its lowest energy level. The excited state is when it's at its highest. The electrons will absorb the energy, so from the electric current, and they absorb the energy. Obviously, to go to the higher energy levels, they absorb the energy. In order to come back down to the ground state, they must emit the same level of energy. No two elements have the same emission spectrum. So the wavelength of light that is emitted is, will tell you what atom is there. Now, there's also elements will emit different wavelengths of light depending on the wavelength of light they absorb. So what they teach in grade 11 is atomic emission spectroscopy. So if we shine light into a sample and at a certain, then we detect light being released at a certain wavelength, that will tell us what is in our sample. Because no two elements have the same emission spectrum. This is how we fingerprint the elements. The reason that they know the sun is made of hydrogen and helium, and it's constantly is because of this atomic emission that is released, and you can look at it through certain microscopes. They pick up the wavelengths of light that are being produced by the sun. Yeah. That's pretty much it for the emission, atomic emission. You energize the atoms. Again, if we look at the noble gases, they all emit a different color. And you can tell what's what by the spectrum that they emit. Okay, let's jump in and do some mass spectrometry. So I'm going to need my pictures. Anybody know what mass spectrometry is? That's right, not many people. It's an analytical technique that's used to identify anything. Solids, liquids, gases. We can try to use it in organic chemistry to determine the structure of proteins, drugs, lipids. But we ionize the sample. We make positively and negatively charged bits out of it. We separate them based on a mass to charge ratio. And then we detect what comes through the end. And you get a mass spectrometry readout that tells you what you have. So the relative intensity out of 100, which tells you how much of something there is. Relative intensity is how much of it there is compared to everything else. And the mass to charge ratio. And it's basically, we have a library of things that we know what they are, and we've analyzed them and we've found their mass to charge ratio. You put an unknown sample through, and it tells you the mass to charge ratio. It matches against all of the, what's the word? All of your unknown samples, and should be able to tell you what it is. So we have a number of concepts for mass spectrometry that we need to understand. Fragmentation. So when we bombard the sample with electrons, it breaks up into bits. Depending on what it is, will show us what it's going to break up into. When we look at a mass spectrum or mass spectrogram, and I'll show you what it looks like over here. So you can see there. So what you can do here is take, this is ethanoic acid from vinegar. You could take an unknown sample, I don't know what this is, it will give you this graph here. So you can then go, okay, go into the library of everything that's ever been tested, and then try and match it up to that. So that's how we use mass spectrometry to analyze. You will go into more depth with this stuff in grade 12, but year 11 is just a fairly basic introduction to it. I got through that quicker than I thought. All right, let's get a bit ahead of next week for the last 5 or 6 minutes, because I feel like I'm going to spend more time on hydrocarbons. Right, we know what an element is. Element is just a single element off the periodic table. They can be bound to each other. So hydrogen exists as H2, even though there's 2 of them, it's still an element. Monoatomic ions, they have more than one of something bound to itself. Compound, 2 or more elements chemically bound together. So sodium and chlorine and ACl. We have CH4 or methane. What else we got? I need one more example. So, elements, compounds, and we have 3 different kinds of bonding. We have, well, actually we have 4. We have metallic, we have ionic, we have polar covalent, and non-polar covalent. So metallic bonding is obviously between 2 metals. And you have, let's just say it's iron bound to itself. And these are surrounded in a sea of electrons. So the reason that metals conduct electricity, because the electricity can travel along through the electrons. Ionic is when, so between sodium and chlorine, but in actual fact, it's Na plus and Cl minus, because the sodium is in group 1, so it donates its extra electron to go backwards to group 8. Chlorine, being in group 7, accepts an electron and goes forwards into group 8. They're not sharing the electrons. It is a permanent donation of a metal's electrons, and the non-metal accepts it. So ionic is between a metal and a non-metal. Polar covalent. So a covalent bond is where the electrons are shared, but they're not always shared evenly. So polar covalent, H2O, non-polar covalent, CH4. Now let's think back to last week when we looked at the trends of the periodic table. Let's look at the electronegativity. Oh man, my brain is fried. The higher the electronegativity, no, that's a lie. The difference between the electronegativity values is what determines if we have a polar or a non-polar bond. So polar covalent is electronegativity difference of greater than 0.5. So my memory serves me correct. Oxygen is 3.5. hydrogen is 2.2. So there's a greater than 0.5 difference in their electronegativity. If we look at here, if anybody's watching, what's the electronegativity of carbon? And what's the electronegativity of hydrogen? If anyone's playing along with that. No one? Okay. I can't remember what the exact numbers are, but the difference is 0.4. So the number is less than 0.5. So it's a non-polar bond. Now, what does this mean? What does this mean? H2O, oxygen is incredibly greedy. Doesn't like to share. It will steal 2 electrons from hydrogen because we know it only has 1 electron because it's in group 1. And it becomes negatively charged. So this is why we call it polar, because you have a negative pole and a positive pole. Carbon and hydrogen, they play a bit nicer. They share all of their electrons equally. And there's no difference in charge on any of the molecules. This right here, I beg of you to make sure you have that name. If you go and study, especially if you're going to go and do some organic chemistry, get to organic chemistry in grade 12. If you understand this and what this means, you're so far ahead of the game. All right, I am going to leave it there for today. Next week, we are going to start some organic chemistry. We'll do mixtures as well. And this here, when we look at organic chemistry, is probably the most important part. So I will see everybody